Hi, my name is Ali Abedi. Welcome to our virtual talk at SIGCOMM 2020. This is a joint work with my colleagues Farzan, Mohammad, Omid, and Tim. In this talk, I present WiTAG, our battery-free Wi-Fi backscatter communication system. Many today's IoT devices rely on a battery to communicate with an IoT hub or a Wi-Fi router. Unfortunately, the battery life of these devices is typically from only a few weeks to a few months. Changing the batteries of many IoT devices can be very difficult for the end user, especially because some of these devices are in hard to access places. In addition, batteries are pretty expensive. So there are great benefits in designing battery-free communication systems, which make them very attractive for many IoT applications. So, is it possible to get rid of the batteries? The answer is yes. Battery-free wireless communication can be achieved using the backscattering technology. For example, RFIDs utilize backscattering to enable communication between a battery-free tag and an RFID reader. In backscattering communication, a tag reflects the signal coming from a source such as an RFID reader. The tag modulates its data onto the reflected signal. Then, the receiver analyzes the backscatter signal to extract the data transmitted by the tag. The power consumption of these tags is so low that they can harvest their required energy from the wireless signal. Although the RFID technology enables battery-free wireless communication, it relies on readers that are typically bulky and expensive. Instead, can we design a battery-free tag that can be read by Wi-Fi devices? Since Wi-Fi access points are available almost everywhere, researchers have looked at enabling backscatter communication between a Wi-Fi access point and a battery-free tag. However, because Wi-Fi was not designed to work with such tags, Wi-Fi backscatter has become a challenging research problem. In this work, we present WiTAG that enables Wi-Fi backscattering by leveraging frame aggregation in Wi-Fi networks. WiTAG is compatible with all existing Wi-Fi access points, including modern 11AC. WiTAG works with open and encrypted Wi-Fi networks. And finally, WiTAG is battery-free. Before we explain WiTAG, let's quickly review frame aggregation in Wi-Fi networks. A legacy Wi-Fi packet includes a physical header and a MAC protocol data unit or an MPDU. The MPDU includes a MAC header and a packet payload. Since the 82.11 protocol involves many overheads, such as channel access and acknowledgements, the standard has introduced a frame aggregation feature to improve efficiency. In frame aggregation, we put multiple MPDUs inside a large physical packet called an aggregated MPDU or AMPDU. We refer to these MPDUs as subframes. Frame aggregation is now a standard feature on all Wi-Fi devices. Let's review how frame aggregation works in Wi-Fi networks. Suppose that the smartphone has multiple packets to send to the access point. Instead of sending the packets one by one, the phone creates and transmits an aggregated frame. The receiving device, which is an access point in this case, checks to see if the subframes are received correctly with no error. Normally, all of the subframes are transmitted correctly. The access point creates an acknowledgement which contains a bitmap that indicates the fate of each subframe. 1 for successfully received subframes and 0 for the corrupted subframes. Since all subframes were received correctly in this example, the acknowledgement contains 7 ones. When the phone receives the acknowledgement, it can find out the fate of the transmitted subframes. We now explain how WiTAG works. In this example, we have a temperature sensor that wants to transmit its data to a nearby Wi-Fi device. Suppose that the last reading of this sensor is 23 degrees centigrade, which is 0010111 in binary. Let's see how the smartphone can read this data. First, the smartphone transmits an aggregated packet to the access point. When the subframes are being transmitted, the tag embeds its data onto the AMPDU by selectively interfering with some subframes. Specifically, if the tag wants to send 0, it corrupts the subframe by creating interference. On the other hand, to send 1, it does nothing so that the subframe can be transmitted successfully. In this example from the left, the tag corrupts the first two subframes to send 2 zeros. Then, it does not corrupt the third subframe to send 1. Next, it corrupts the fourth subframe, and finally, it does not corrupt the last 3 subframes to send 3 ones. When the access point receives this aggregated packet, it finds out that some subframes are not decodable. It then creates an acknowledgement for this packet. Interestingly, the bits in the acknowledgement exactly match the tag's data. When the smartphone receives the acknowledgement, it can extract the tag's data directly from the acknowledgement. The beauty of this approach is that the Wi-Fi access point is not even aware of the procedure we just described. It simply receives an aggregated packet and sends back an acknowledgement, which is part of the normal operation of Wi-Fi. As a result, no modification is required on the access point. We have evaluated the performance of WiTAG under different scenarios. We now present some of these results. We have conducted a series of non-line of sight experiments. This is the floor plan of our experiment setup. The access point is placed at one location and the tag and Wi-Fi client device are moved to different locations. The distance between the tag and the client device is 1 meter. We have measured the bit error rate and throughput at 10 different locations. The experiment shows that WiTAG can achieve a bit error rate of about 1% or lower in all locations. In most locations, the throughput is about 4 kilobits per second, except location J, where the throughput is around 3 kilobits per second. Location J is 18 meters away from the access point and behind a concrete wall. Although the locations we tested in this experiment are behind metal barriers or multiple walls, WiTAG shows a robust performance in all locations. In the next experiment, we evaluate the performance of WiTAG in terms of message success rate under 4 different scenarios. In these experiments, the tag sends its data every 10 seconds, and the experiment length is 17 minutes. In scenario 1, we measure the message success rate when there is a lot of background Wi-Fi traffic on the channel. Despite the busy channel, the tag can successfully deliver all of its packets. In the second scenario, in addition to the background traffic, we add 2 Wi-Fi devices that stream videos from YouTube. Although we inject more traffic, we observe no difference in the message success rate. We repeat these 2 experiments now with 2 tags. The experiment shows that the 2 tags achieve a message success rate of at least 92% despite the very busy wireless channel. In scenarios 2 and 4, we also monitor the video stream to see if WiTAG causes any problem for these clients. We observe no degradation in the quality of videos for any of the 2 clients. This experiment shows that WiTAG can support multiple tags with minimal impact on other devices. In this talk, we presented WiTAG, which enables Wi-Fi Backscatter Communication by leveraging 82.11 frame aggregation. WiTAG is fully compatible with existing modern Wi-Fi access points without requiring any hardware or software modifications. WiTAG works with encrypted and open Wi-Fi networks. I hope you have enjoyed this talk. Thank you.
Thanks, Eddie, for the great talk. It was a pleasure. There are already questions coming in for you, so I'm just going to read one of those.
Sure.
So the first question is from Syed Saad Afzal. His question is, so WiTAG works by detecting the corrupted MPDU subframes, but one question here is that would this approach still work if we were to use it near devices which cause direct interference in the Wi-Fi frequency band? Example devices such as ZigBee, cordless phones, microwave, etc.
That's a good question. So I answer the Wi-Fi part first. So if there are other Wi-Fi devices, does WiTAG create interference for them? Because that's how it communicates its data, right? So that's a very good question. So the way we make sure that nothing is happening at that time is the way the synchronization mechanism works. You can see more details in the 20-minute video. So what happens is that the client device that wants to read the data starts sending some packets around the time when it expects the tag to transmit its data. So basically, the client device starts to occupy the channel around that time, right? So in most cases, it's our device that's sending data, not others, because others will probably push back their transmission or something like that. And also, too, I have to say that there are restrictions in terms of where the tag is. So if one of these two devices is like very far from the tag, like if, for example, we have a neighbor network, right? They are behind the wall. Both of their devices are behind the wall. The tag won't impact their transmission at all. So these two are basically the mechanisms that we use to make sure we don't cause interference. And I don't know, the second part was that how can we detect interference from other sources?
Yeah, like ZigBee, cordless phones, microwave.
Yeah. So like any physical layer, we need some error detection mechanism to figure out that if this corruption, if this bit is really 0 or not, right? So it's like any other physical layer. So we need to add some basically error detection mechanism.
Makes sense. So the next question is actually a question from a couple of people, from Yeshong and Shadi Hassan. And the question is, do you evaluate the damage of your tag to normal Wi-Fi transmissions? Because the solution may hurt the normal transmission and cause a lot of packet drops. If the user is running applications like video conferencing, the high packet loss may result in QoS decrease. Do you evaluate that?
Yeah, that was basically tested by the very last graph that we showed. So in two of those scenarios, we had two Wi-Fi devices that are not part of our experiments. They are just streaming video from YouTube. And then WiTAG communicates its data with other devices. And we saw no performance issue for those two devices that were streaming video. And the reason is that the time WiTAG occupies channel is minimal, right? It's like a matter of milliseconds in every 10 seconds that it wants to transmit, right? So the time it occupies is very small.
Makes sense. Awesome. So there are a few other questions, but I think we can move to Slack for those questions in the interest of time. Thanks a lot for your talk. It was really amazing.
And there are quite a few questions on the Slack channel. First of all, Sadi Hasan asked about how does the WiTAG affect other clients on the Wi-Fi network?
Thanks. This is a good question. So WiTAG sends its data by corrupting subframes. So how does that impact other devices, right? We have measured this, right? And before that, let me explain that when the tag wants to transmit data, the client device starts sending messages back to back for a short period of time so that we occupy the channel and prevent others to send packets during that time. This minimizes the chances we corrupt an unwanted packet during that time. And we have tested this, like the last plot that we talked about, it shows that we have like minimal impact on other devices. We intentionally put two other devices very close to the tag. These are not supposed to be corrupted, and they play video. And we did not see any impact on these devices.
Thanks for your response. And the second question is, how do you make sure the corruption is due to tag transmission instead of background interference or other noise?
This is another great question. So what we do, the client device tries to use a transmission rate that is pretty robust, so that if there's no tag, the chances of having a corruption is very small. But although we make this assumption, there's still a chance that some packets are corrupted because of other reasons, such as path loss and interference from other devices, like a microwave oven, right? So, like any other wireless communication system, WiTAG also requires an error detection mechanism to find these unwanted errors. So if a bit is flipped, we have to be able to detect it. So we need an error detection mechanism like a parity bit or more complicated systems to detect these errors and correct for them.
Thank you so much. In the interest of time, we will move the remaining question to the Slack channel. Thank you very much, Ali.
My pleasure.